Hello, Geography 212 students. I'm going to run you through some of the highlights of Chapter 8, and it's entitled Wind and Weather. The first thing it talks about is the air pressure gradient. You can find this as isobars on a surface analysis map. We also do it on upper air charts, which we'll have a look at later on in the course. So we get an air pressure gradient whenever there's a variation in the air pressure between two horizontal locations. And again, you can see this on our surface analysis maps. You've already done a lot of this, and you'll know that by convention, these isobars are drawn at 4 millibar intervals. Now, that's the horizontal pressure gradient. There is also a vertical air pressure gradient. And we know by now that the air pressure decreases with altitude. So there's an air pressure gradient from the surface of Earth upwards. In other words, air wants to blow from the surface of Earth upwards because of that air pressure gradient. But because of Earth's gravity, it withholds that. It keeps the air closer to the surface, and we don't see the air or in the atmosphere leave the planet. When we measure air pressure gradient, it's measured perpendicular to the isobars, and the closer together these isobars are, the greater the pressure gradient. So you can see that here. If you look at A, you'll see that these isobars are more closely spaced. That means there's a greater pressure gradient. That means, therefore, there will be stronger winds blowing perpendicular across these isobars. If you look down at B, you'll see that these isobars are more widely spaced. Air pressure change is more gradual, and weaker pressure gradient, therefore a lighter wind. So that when you're looking on a surface analysis map, it's very easy to quickly see what areas of the United States or any location would have the strongest winds. Just look for the locations where we have the most closely spaced isobars. Now, there's another effect that acts on horizontal wind on the planet, and this thing is known as the Coriolis Effect. And it's because the Earth is a sphere, and as the Earth turns, you can see that if you take a look at the right-hand side, you can see that what's going to happen is any air moving, say, from west to east along the red line there is going to be deflected to the right in the northern hemisphere. All right, so this is a Coriolis effect. Air is deflected to the right. Now, what effect this has on wind patterns, you can see from this slide here. So the Coriolis effect, then, we can see on a globe here. If air is traveling to the west in the northern hemisphere, it's deflected to the right, which is the north. And if air is moving east toward the east in the northern hemisphere, it's deflected to the right in the south. Another thing to consider here is that as we get further from the equator, either north or south, the Coriolis effect is greater, meaning that wind is deflected even more. If you're right on the equator, there is no deflection because of the Coriolis effect. All right. Now, in terms of meteorology, the last bullet I've got there, you can see that the Coriolis effect really only significantly influences wind in very large scale weather systems. So in terms of small scale stuff, it really has no effect. Okay. Friction. This is an important concept in meteorology. And basically, if you look at this second bullet down, we have an area of meteorology we call boundary layer meteorology. And what's that? Boundary layer in meteorology refers to the zone of the atmosphere that is in contact or close contact, near contact with the Earth's surface. In other words, it encounters friction. So when we have the atmosphere closer to the ground, it encounters friction, and a lot of things can happen. Turbulent eddies, all kinds of things. But as we get higher up, and generally we call it about 1,000 meters or about 3,300 feet in elevation above ground level, friction becomes a minor force. And we'll see this later on when we start looking at upper air charts. We'll see how differently really the upper airflow is compared to our boundary layer atmosphere. All right, so just recall that, remember that then. The boundary layer in meteorology refers to the atmosphere within 1,000 meters of Earth's surface, 3,300 feet, and a lot of eddying and different things can happen to the wind down there. It gets very complicated. Something called hydrostatic equilibrium. I think I talked about this earlier at the beginning of that lecture here. It's just what it is. Again, we have this vertical pressure gradient force. In other words, as we ascend from Earth's surface, the air pressure decreases. Therefore, we have a gradient. In other words, there's higher pressure at the surface, decreasing pressure at altitude. So therefore, wind wants to flow that direction. However, we have this force is counteracted by gravity, so our atmosphere reaches an equilibrium. We don't lose our atmosphere because of gravity, and that's referred to as hydrostatic equilibrium. Okay, this is just a pictorial, something you've been doing for weeks now on some of your exercises. Highs also introduce a new term here. High pressure systems can also be called anticyclones. So cyclonic flow in the northern hemisphere is counterclockwise. So it just stands to reason that anticyclonic flow, or an anticyclone, is going to flow in a clockwise manner. All right, now low pressure systems are simply referred to as cyclones. Now, to get a little more detailed, cyclones in the northern hemisphere, say in mid-latitudes across the United States, are referred to by a couple of other names as well. They're referred to as extratropical cyclones. That extratropical simply means outside of the tropics. They're also referred to as mid-latitude cyclones. I tend to refer to them only as low-pressure systems. I think that's an easier terminology to identify, okay? So high-pressure systems are anticyclones. Surface winds are blowing clockwise and outward. Low-pressure systems are cyclones with the surface winds blowing counterclockwise and inward. This is just reversed in the southern hemisphere, okay? You can see that right there. Some other terminology I'm going to introduce here, and we'll be using this quite a bit more again when we get into upper air charts. This is just a typical surface analysis you're looking at here. We will refer to high pressure systems as areas of ridges. Okay, and we refer to cyclonic areas as troughs. So in meteorology, you're going to see this kind of terminology used. We'll talk about a ridge of high pressure moving in, or we'll talk about a trough of low pressure moving in. And more on this later. It'll become a lot easier to identify on a surface analysis, okay? So how do we measure the wind? Well, there's several different ways to do it. But first of all, wind velocity is a vector. It has a magnitude and a direction. We already know that. Wind is definitely distinguished between horizontal and vertical components. And up until about 1985 or so, we weren't really measuring the vertical component at the surface. We certainly are now. More on that later when we get into violent weather. But typically, the vertical air motion is as much as a very small fraction of the horizontal wind speed. So generally speaking, the horizontal wind speed is a great deal more than any kind of vertical wind speed, but that can be different. We can get a significant vertical component of wind speed in things like thunderstorms, but more on that later. Okay, and third bullet down, you know that wind direction is a direction it's coming from, not blowing toward. There's many different instruments several anyway, instruments that we use to measure the horizontal wind speed. We have wind vanes, and there's pictures of all this stuff in your textbook. Take a look at it unless you're already familiar with it, okay? Wind vanes, wind socks, typically see those out at airports, that kind of thing. And then we can also, the last bullet down, if you don't have any of these instruments to use, you can estimate the wind speed by using the Beaufort scale. That's in your textbook. You can have a look at that. Again, here's some of the instruments we use to measure wind speed. Cup anemometers, they're probably the most common. Hot wire anemometers, these are less common. Aerovanes, that's where we have the wind speed and the wind direction all on one instrument. And then, we have a sonic anemometer, and you can, again, find pictures of these in your textbook. Now, something for measuring the wind, we do have pretty strict protocols from the National Weather Service on this. And to measure wind, to get a official wind direction and wind speed, the protocol is that instrument needs to be 33 feet above the ground. The thing about sighting weather stations, you look at the photograph of this one here, the problem is I guess security from what my experience. I have set up many weather stations over the last several decades. Okay, and the problem really is security. You can see the fence around this one, and that's a fairly decent fence. But what we tend to do at the college here, we have weather stations at all the locations for Yavapai College, but we've mounted them all pretty high on rooftop locations, and it's all about security. That's the only reason. So those wind directions and wind speeds that you read off of our weather stations, they're not going to be used as official wind speeds. Okay, so to be official, you must be 33 feet above the ground. Second bullet down, radiosondes, particularly radiosondes. These would be balloons filled with hydrogen now instead of helium. I don't know if you guys are aware of this, but there's a worldwide shortage of helium. So we've had to go back to use hydrogen inside our weather balloons. We don't like it because hydrogen is a very can be a very explosive gas. Helium is inert, so we don't have to worry about it exploding. But yeah, worldwide shortage of helium. Anyhow, then later on we'll get into radiosondes more. You've already looked at one of your labs was taking a look at a vertical profile, the one above San Diego. And so radiosondes will go up and give us measure wind speed and wind direction in the upper atmosphere. This chapter 8 refers to scales of weather systems, and you're going to see some of this terminology throughout. If we start with the planetary scale, very large scale in terms of space and time, this could actually be the size of the planet. So we could refer to weather systems the size of the planet. The time scale on something like that is weeks to a month. And one example that's given there are trade winds. The trade winds they circle the Earth, so that would be a planetary scale meteorological phenomenon. We get a little smaller, we come down to what's called the synoptic scale. And the synoptic scale is going to be something like 1,000 to 3,000 kilometers. This would be a weather phenomenon that could last days to a week. And one example they're giving you here is an Arctic high. This would be some continental polar air that would, say, move down into the United States, typically in the wintertime. Okay. Next scale down, getting smaller, is mesoscale, 10 to 1,000 kilometers, hours to a day. This is going to be something that affects regions and just local weather. And an example given there would be a thunderstorm. In this case, they're talking about a severe thunderstorm, but just a thunderstorm. And then finally, we get down to the smallest scale, which is microscale weather phenomena. And that would be a meter to 10 kilometers in scale. This could be something that lasts in a very short period of time, up to maybe an hour. A good example for this is a tornado. For example, the residence time of a tornado on the ground is really just a matter of a few minutes, maybe even just seconds. All right. So those are the different types of scales that we talk about when we refer to different weather systems. All right, well, that's going to conclude my short little lecture here for Chapter 8, and we'll see you next time.